Hello, this is problem set number 3, problem 1. During the time 0.305 moles of an ideal gas undergoes an isothermal compression at 22 degrees Celsius, 392 joules of work is done on it by the surroundings. Part A, if the final pressure is 1.76 atm, what was the initial pressure? And part B, sketch a PV diagram for the process. Okay, so real quick, I'm just gonna bring up the things that I find useful to know. All right, I have these in my notes from the lectures, and is some things that I think might be good to have on your cheat sheet. And the first one is anything in degrees Celsius. To convert to Kelvin, you would need to add 293 to whatever temperature is in Celsius, and you have your temperature in Kelvin. All right. The second thing to know is 1 atm is equal to 1.01 times 10 to the 5th pascals. Third thing is that the constant R is equal to 8.31 joules per mole over joules per mole times Kelvin, and it is also equal to 0.08206 liters times atm over moles times Kelvin. And these two are equal to each other, they just have different units in the numerator. So you're going to choose which constant for R you want, depending on the units you want to cancel out and the units given in the problem. All right, the next thing is whenever you have the unit in joules, that is also equal to the unit kilograms times meters squared over seconds squared. Same thing with pascals. When you have pascals, that the unit pascals is equal to the unit kilograms over meter times second squared. Also in chapter 19, we do know that work environment is equal to negative work of system. So the work done by the environment is equal to the negative work done by the system. They're equal, they just have different signs. Okay, and lastly, e to the power of natural log of x is equal to x. Okay. All right. So again, let's write down the things we know from the problem. So we know that we have 0.305 moles. Okay. We have an ideal gas, right here. Undergoes isothermal compression. So isothermal means temperature doesn't change. So isothermal compression at 22 degrees Celsius. So whatever your initial temperature is also going to be your final temperature. Let's call that T2. And so since they're equal, let's just call it T, and that will be 22 degrees Celsius, right? And I'll go ahead and convert that to Kelvin using this formula right here. So I'm going to add 293, and that's going to be equal to 295 Kelvin. All right. What else do I know? There's 392 joules of work done on it by the surroundings. So work environment, right, or work done by the surrounding is equal to 392 joules. Again, we know that whatever the work environment is just negative works done by the system, right? All right, so for part A, if the final pressure is 1.76 atm, what is the initial pressure? So we're also given that P2 is equal to 1.76 atm. Okay. And one second. And for part A, we want to know what is the initial pressure? What is P1 equal to? All right. So let's see. Using we know that it is isothermal, right? Isothermal compression, isothermal compression right there. All right. Let's use the ideal gas law. So that is PV equals nRT, right? It's isothermal, so I know that temperature is constant. R, that's always a constant, right? That's this guy. I just want to make sure I'm recording my voice. Hopefully I am. Okay, and then moles, that's 3.305, that's going to be constant. So everything on the right side of the equation are constants. Right? And if these guys are constant on the right side of the equation, that means that if for my initial state and my final state, P1 V1 is equal to the constant nRT. Actually, I'll write that in a different color so it's clear that these are constants and equal, right? And for the final state, my pressure 2, volume 2, is also equal to the same constant, nRT, right? Because they don't change, they're constant. So as a result of that, I know that P1 V1 equals P2 V2, right? Therefore, P1 V1 equals P2 V2. Okay. I also know that let's use what stuff do I have to use if I want to use the ideal gas law, right? So PV, the ideal gas law, right, is PV equals nRT. Okay. Let's check some of the things I have. I know N, it's given right here, so I got this. I know R. T I have, that doesn't change, it's isothermal. And I know P2, right? So because I know P2, I'm going to use the final state. I'm going to use the ideal gas law for the final state. So P2, sorry. For this, I know P2, right? That's given. Okay. So I can try to find my V2, right? So P2 is 1.76 ATM. I need to convert it to pascals to use it in the ideal gas law. So real quick, I'm going to convert P2 to pascals. So 1.76 ATM, which is my P2. I'm going to multiply that by, I'm going to cancel out ATM. So 1 ATM is equal to 1.01 times 10 to the 5th pascals. And that's going to equal to 177 and 760 pascals. So that's going to be my P2. So this is equal to 177, 760 pascals. Okay. So again, I'm gonna just rewrite my ideal gas law with the things I know. So P2 is 177,760 pascals. I want to find my V2, right? Because this is the final state, the equation for the final state. V2 is equal to N, which is 0.305 moles. R, which R would I want to use? I have Kelvin, I have moles, I have pascals. I'm going to go with joules over mole times Pascal. Okay, so I'm going to use 8.31 joules over mole times Kelvin. Did I say Pascal? I meant to say 8.31 joules over mole times Kelvin. All right, and my temperature doesn't change. It's 295 Kelvin. I'm going to move this guy here. I just basically converted my pressure in ATM to pascals, to pressure in pascals, right? Okay, so now I can solve for my V2, or my volume at the final state. That would be, or actually before I do that, I'm going to go ahead and use these two knowns to convert my units from joules and pascals to their equivalents. Okay, so this will be 177, 760, and instead of pascals, I'm going to use kilogram over mole, or over meter times second squared. So kg over meter times second squared. V2 is equal to 0.305 moles times 8.31, and instead of joules, I will convert right here to kilogram times meter squared over second squared. And I'm not going to forget my moles times Kelvin on the denominator, so mole times Kelvin, and times 295 Kelvin, okay? So I could move everything to the right side and leave my volume at the second state on the left side of the equation. And my units are going to cancel out, and if I plug all that in the calculator, basically divide both sides of the equation by 177, 760 kilograms per meter times second squared, I would find that my volume at the final state, or second state, is 0.00421 meter cubed. Okay, so I have this now. All right. And for an isothermal process, right, which is what we have right here, isothermal. What do I know? For an isothermal process, right, on our notes and in the chapter 19 summary in the video that I posted, we know that, let's write that with a different color. For isothermal process, work done by the system is equal to nRT, which are constants, times the natural log of V2 over V1, right? Then we can continue to solve from there. And if you don't know how we got this, I can quickly run through it, but I'll do that at the end. Anyways, for isothermal process, we should know that this is the equation for work done by the system, okay? So what is my work done by the system? I know the work done by the environment, right? That's given right here. And given in the equation, 392 joules of work is done on it by the surroundings. So I know that work done by the environment is equal to the negative work done by the system. So I have my work done by the system is negative 392 joules. Okay, and that is equal to N, which is 0.305 moles, times R, which is 8.31 joules per mole times Kelvin, times 295 Kelvin. That's my temperature in Kelvin. And times the natural log of V2, which is 0.00421 meters cubed over V1, right? I don't know what my V1 is. Okay, so I'm going to put everything that's this guy, and this guy, and this guy on the left side on the right side of the equation, and I'm going to move this guy on the left side of the equation because that has our unknown. Okay, so I bring this down. That is that the natural log of 0.00421 meters cubed over V1, or our volume in the initial or first state, is equal to, can I erase this so I could have some space, minus 392 joules divided by (0.305 moles times 8.31 joules per mole times Kelvin times 295 Kelvin. All right. And my units would cancel out, and I would have the natural log of 0.00421 cubic meters over the volume at state 1 is equal to 0.524, right? And I can get rid of the natural log using this thing that is useful to know, and that is e to the natural log of x is equal to x. So I'm going to go ahead and say e to the natural log of 0.00421 cubic meters over V1 is equal to e to the 0.524. Okay? And so, as you can see, this will cancel out with the natural log. So I have 0.00421 cubic meters over V1 is equal to, if I plug this in the calculator, e to the power of 0.524 is equal to 0.59198. okay? And so solving for V1, I would get V1 is equal to 0, would be 0.00421 cubic meters divided by 0.59198. So therefore, V1 is equal to 0.007105 cubic meters, okay? My sig figs are not accurate, but I'm just trying to solve the problem and provide some more understanding towards it. All right, so now I've got my V1 and my V2, and I know my initial pressure, or no, I'm looking for my initial pressure, and I know my final pressure. So I'm going to go back to this equation right here, right? And again, I know I'm looking for my P1. I just solved for my V1. Final pressure, or pressure at state 2 is given, and we also solved for V2 earlier, right? So then now we can just solve for P1. So let's actually bring that down. Copy, paste. All right. So again, because nRT is constant, right? We have isotherm, so T is constant, R is constant, and N is constant. And looking at the initial and final states, if we have P1 V1 equals nRT, which is a constant, and P2 V2 equals nRT, which is also a constant, I will have, therefore, P1 V1 equals P2 V2. All right, and let's plug in what we know. So I'm looking for P1. V1 we said was 0.007105 cubic meters. And that is equal to P2, which was given right here. Okay. So that's P2 is 177,760 pascals times 0.00421 cubic meters, right? That's our volume 2 that we solved right there. And so we find that P1, plugging this in the calculator, right? We find that pressure at state 1 is equal to 1.05 times 10 to the third pascals. Okay? And you could leave it at that, or if you want to leave it in ATM, then that is equal to again 1 ATM is equal to 1.01 times 10 to the 5th pascals, right? Yep. And that will equal to 1.04 ATM. All right. So I don't know if you want to leave it in pascals or ATM, but either way, that is your pressure at state 1. And that is what we were looking for part A, correct? Initial pressure, yep. All right, so let's sketch a PV diagram for the process. Okay, so for part B, PV diagram. All right. So the This is volume, this is pressure, axes. All right, it's just 0. All right, what is our initial pressure? 1.04 ATM, and final pressure is 1.76 ATM. So, oops. Initial pressure is 1.04 ATM. P1 equals 1.04 ATM. And P2 is equal to, it was given as 1.76 ATM. Okay. And volume, our volume 1 was 0.007105 equals 0.007105 cubic meters, and volume 2 is equal to 0.00421 cubic meters. Okay. And so our P1 V1 and P2 V2 this is our first state and this is our second state. So our path between states would look something like that. Oops, that's quite bad. And it would go in that direction. Okay, so that's the PV diagram for part